Good morning. How is everyone? Show me your hands if you're terribly jet lagged. Show me your hands if you're local. Okay, now I've identified the drinkers. All right, so this is the talk on the do's and don'ts for Ceph and OpenStack. My name is Florian. I run professional services and education at City Network. Some of you may know me from prior summits when I presented as CEO and principal consultant at Stexo. We've just been acquired by City Network just last month, and I'm happy to say that this is already the second time that I get to present in my new role in an absolutely gorgeous city. It was Copenhagen 2 weeks ago, and now Sydney, which is great. This is my 9th OpenStack Summit, and if my count is accurate, my 16th presentation, and I finally get to have a full-length talk about Ceph, which for some reason I've never been able to do at an OpenStack Summit before. So I'm going to talk about Ceph, which is pretty much everyone's favorite software-defined storage, and specifically Ceph as it integrates with OpenStack. Now, I probably don't need to reiterate that this is an extremely popular combination. These are the numbers from not the latest OpenStack user survey, but the one from April. These are the stats for Cinder, showing that Ceph RBD is the single most popular backend by a relatively large margin for Cinder storage. Just for the record, the user survey doesn't come with any such specific stats for Glance or for Nova ephemeral storage, but it's reasonable to assume that if a cloud operator uses a Ceph cluster with RBD for Cinder, that they're quite likely to use it for other OpenStack services as well. For those relatively new to Ceph or relatively new to OpenStack or both, Ceph RBD allows us to integrate with OpenStack on several different levels or several different parts of OpenStack, specifically with Glance, our image service, with Cinder, our volume and persistent block storage service, and with Nova, our hypervisor management. Now, I'm not going to go into too much detail about how this is done. I'm not going to go into too much detail about how you deploy Ceph in an OpenStack context or how you make your OpenStack cluster talk to your Ceph cluster. First, because there's plenty of splendid documentation on that out there. Secondly, because it's also very well integrated into a number of deployment automation schemes. Basically, no matter what you use to deploy your OpenStack, it will come with an automated way of seamlessly integrating a Ceph cluster. And it doesn't matter whether you're deploying with OpenStack Ansible or whether you're deploying SUSE OpenStack Cloud or whether you're deploying an Ubuntu OpenStack Cloud with Juju, they all come with a very, very polished and nice Ceph integration. So as I said, I'm not going to spend any time on this talk on how this is done, on how we actually make OpenStack talk to Ceph or vice versa, but I am going to talk about some specifics that you should take into consideration when configuring your OpenStack services for talking to a Ceph cluster. And I want to start with Glance because that's very simple and easy to explain. So with Glance, obviously, you have the ability to define and also use multiple image stores. One of those stores that we've had in there for quite a while, I believe it landed somewhere around the SX or maybe even Diablo timeframe, is the RBD store, which has Glance store images in Ceph RBD images in a Ceph cluster. So basically what you do there is you define an RBD store in your Glance configuration, and you then set presumably the default store in Glance to RBD. And then there's a few other things that you want to do. Most of these things, again, are things that your deployment automation will happily do for you. If you rolled your own, or you just want to verify what your deployment automation actually sets, here are a few things that you might want to look into. So one of the things that you always want to use for a variety of reasons is you want to enable the Glance v2 API. And in a Ceph-based Glance environment, what you also want to do is you want to enable the show image direct URL configuration option. What that does is exposes the backend storage URL basically a pseudo URL or a pseudo URI format, which starts with RBD in the RBD case. It exposes that to Glance clients. In other words, it instructs your client about the fact that Glance is RBD backed and what the specific backing of a specific Glance image is. Now, when you do that, you enable your applications to make use of RBD clones. So in RBD, you have this ability to create clones. You can think of a clone as a writable snapshot, more or less, so or the writable siblings of snapshots, which in RBD parlance are read-only. So broadly simplifying here, a clone creates Ceph RADOS objects only for those parts of your block device that have been modified relative to its parent snapshot. And that means two things. One, you save space. That's kind of a no-brainer, but in and of itself, it's not very compelling because storage space is rather a cheap thing. But anything that's not been modified in the clone can be served from the original volume, and that's kind of important because it means that you're essentially hitting the same RADOS objects and thus the same OSDs no matter what clone you're talking to, and that in turn means that those objects are likely to be served from the respective OSDs page caches, in other words from RAM, and RAM is always faster to serve than any persistent storage device, so being able to serve reads from the page cache is a good thing. So that in turn means that serving data from a clone, the unmodified data that was in the original volume, will be faster than serving that same data from a full copy of a volume. So just as an example, when Cinder is configured to use the Glance v2 API, open parenthesis, it normally is these days, and you have show image direct URL enabled, and you are creating a Cinder volume, a bootable volume from an image. Remember, there's this thing that in Cinder you can either create just an empty volume, or you can create a volume that's based on another volume, or you can create a volume that's based on a Glance image. In a default configuration, what Cinder will do on your behalf is it will actually talk to Glance, download that image, and then upload it into its own store, whatever that is. If both Glance and Cinder use RBD, then you can use that cloning in the background, which makes this thing infinitely faster. So rather than, say, for example, shuffling 20 gigabytes worth of image data around and moving them into Glance, and moving them into Cinder, Cinder can simply say, oh, okay, so this thing uses an RBD backend, I use an RBD backend, and so I'm just going to clone this thing in the backend that's much faster and brings a VM up really, really quickly. Going from persistent storage in Cinder and how it relates to Glance, we also need to talk about ephemeral storage and how it relates to Glance. And there, one thing that you typically do when you're running a Ceph cluster that talks to your Nova, you would set libvirt images type, or the images type option in the libvirt section of your nova.conf to RBD on your Nova compute nodes. So that would look roughly like this. And the default type here is disk, which means that when you fire up a new VM, what happens is Nova Compute on your hypervisor connects to the Glance API, looks up the desired image, downloads it onto your compute node, and then creates a QCOW2 copy, which uses the downloaded image as the backing file. And that process uses up a fair amount of space on your compute nodes, and it can quite seriously delay the spawning of new VMs in case it's been scheduled to a host that hasn't downloaded and thus cached the desired image before. That's a little silly if you already have RBD in your Glance backend, because if you just flip images type to RBD, then Nova ephemeral storage will also use this kind of cloning in the backend to much faster spin up VMs from Glance images and also save storage space in the process, which is generally a good thing. You always essentially want to enable RBD caching on Nova compute nodes. So librd, that's the, librd, that's the library that underpins the QEMU KVM RBD storage driver, can enable a disk cache that uses the hypervisor's host RAM for caching purposes. Now that sounds dangerous, but it's not. You should totally use this. It's a cache that is safe to use. So on the one hand, the combination of virt.io block with the QEMU RBD storage driver will properly honor disk flushes. So that is to say, when an application inside your VM says, I want this data on the disk now, then virt.io block and QEMU, KVM, and Ceph will all conspire to only report that write as complete when, one, it's been written to the primary OSD, it's been replicated to, two, it's been replicated to all the available replica OSDs, and three, the write has been acknowledged to have hit at least the persistent journal on all of our OSDs. So that's a good thing. And then in addition, Ceph RBD has a very smart safeguard in place, which is even if it's configured to operate a cache in write-back mode, it will refuse to do so, meaning it will continue to operate in write-through until it has received the first flush request from its user. And in the virtualization use case, that's a VM that sits on top of it. And so, therefore, if you have a VM that just never does that because it's been misconfigured or its guest OS is just age-old, then what RBD will stubbornly refuse to do is caching writes. So it just won't cache the writes. It will operate in write-through mode until it gets that first flush, and from there it can then switch into write-back mode because it realizes, okay, there's someone above me that knows what they're doing. You can enable this write-back caching for Ceph by setting this Nova Compute configuration option. It also goes into the libvirt section. You would typically already have set images type RBD, and then you set this cache modes to network equals write-back, and that enables write-back for network-based devices, such as Ceph RBDs. And you generally always want to do that. Again, this is something that a lot of deployment automation facilities do for you automatically. Another thing that you absolutely will want to do is you want to separate your Ceph pools, your RADOS pools, for images and volumes and ephemeral disks. So if you enable show image direct URL equals true in Glance, and you configure Cinder and Nova Compute to talk to Glance using the V2 API, and you've configured Nova Compute with libvirt images type RBD, then all of your VMs and volumes will be using RBD clones. And what's nice about clones is that they can span multiple RADOS pools. So that means that you can have an RBD image and its snapshot in one pool and clones in another. And you should totally do that for several reasons, because firstly, you can separating your pools means that you can lock down or restrict access to those pools separately. That's just a standard threat mitigation approach. So if your Nova Compute node gets compromised, and in whichever way, and the attacker can corrupt or delete ephemeral disks, then that's kind of bad, but it would be bad if they could also corrupt, that is, overwrite your Glance images. And if you set your capabilities correctly, then if you separate your pools, then you would be unable to do that. Separate pools also means that you can have different pool settings, such as the settings for size, that is the number of replicas that we have for every RADOS object in the pool, or the number of placement groups in the pool, and a few other configuration options. And most importantly, separate pools can use separate crush rules. And we'll get back to that in a second because it usually comes in handy. So what is common to do is you have at least 3 different pools, one for your Glance images, that's usually named Glance or images, one for your Cinder volumes, that's usually named Cinder or volumes, and one for your VMs, which is typically called either Nova Compute or VMs. And then in some configurations, you would also use a separate pool for Cinder backup. But those 3 essentially you always have. Most deployment automation schemes give you deployment automation facilities give you the option to toss everything into the same pool. That's not a great idea for a number of reasons. You just want to use these 3 different pools, at least 3 different pools, and be happy with that. The next thing that I'm going to get to, I don't want to even get to in that much detail because it's kind of a religious discussion to have, and that is about, should you be using SSDs for your Ceph OSD journals? My take on that is a bit ambivalent. On that, I can only give sort of the standard consultant answer, which is it depends. There is a lot of documentation out there and a lot of recommendations out there that say you should always use them. My point on that is you should be applying sort of the arithmetic to the problem here. So suppose, because there's this rule of you should be using separate journal devices that are SSDs that, as a rule of thumb, use a ratio of 1:4 to 1:6 to the spinners. But if we look at that, then suppose you've got you're following the 1:6 approach, and your SATA spinners are capable of writing 100 megabytes per second, And that's 6 spinners, that makes 6 OSDs, and each OSD uses a journal device that is a partition on an SSD. And suppose further that that SSD is capable of writing at 500 megabytes per second, then you've just made the SSD your OSD bottleneck, because you can literally not hammer all of your disks simultaneously, because they would be capable of writing at 600 megabytes per second in aggregate, and you can only write at 500 megabytes per second to your journal. So it's simply something that you want to be diligent, and you want to be diligent about, and want to work out. And by the way, in that scenario, you would be doing just fine if you're operating on a 1.4 ratio, but make your spindles just a little faster, and the SSD performance advantage goes out the window again. So you do need to plug your own numbers into this, and you do need to make your own evaluation for price and performance. Just don't assume that using journal SSDs will be a cure-all that is not going to cost anything, because there ain't no such thing as a free lunch. And by the way, this is also changing in a way, or quite significantly, with the advent of BlueStore, which is the new object store backend that we're using for Ceph OSDs with the recent Ceph Luminous release and moving forward. One thing, by the way, that your journal SSDs won't help with at all are reads. So if you want to take advantage of the low latency of SSDs on reads too, then you can just make the SSDs OSDs. So not OSD journals, but actual OSDs with a store and a journal, or BlueStore and a write-ahead log. And what that will create is OSDs that don't just write fast, but read fast as well. Now, it may be considered relatively luxurious to run a Ceph cluster of petabytes in size with just SSDs or just NVMe devices. So most of the time, or most Ceph clusters out there, will be using a mix. And when you have all-flash OSDs, then you can treat them specifically or separately in your Ceph cluster. And how you do that, or how you can do that, is actually slightly different between Ceph Joule and Ceph Luminescent moving forward. In Ceph Joule, you would put your all-flash OSDs into a separate crush root, so you would have a separate hierarchy of crush devices, and one of them would entail all of your OSDs that are spinners, and one of them would entail all of the OSDs that are SSDs. There is a new feature in Luminous, and my apologies to all fans of BlueStore. This is probably my favorite feature in Luminous. It's called device classes. And in device classes, you can greatly simplify the crush rules that you write in order to use your fast OSDs. So this is what this would look like in Joule. In Joule, you would have to have like 2 rules that use 2 separate root hierarchies. The one at the top would use default, and then the one at the bottom would be called hyperf or something, where then all of your hosts are in there, duplicated with just the SSD OSDs in them. And in Luminous, that is much easier, because now we don't say step take default and step take some other hierarchy, but we just say step take default class HDD, class SSD, or class NVMe, and we can also devise other device classes. And what's really neat about this is that Ceph OSDs will go to great lengths to automatically identify and auto-tag devices as you spin up your cluster. So your Ceph cluster will basically be aware by itself of which of your disks are spindles and which spinners, and which of your disks are SSDs, and which of your disks are NVMe devices, and then you can write your crush rules like that. And oh, by the way, there's also now there was already a command line tool where, rather than hacking your own crush map, you could create simple rules with one command on the command line, and that has also been extended to now support these device classes. Like I said, if I were to choose one favorite feature in Luminous, this would be it. Now you've got these rule sets. And you've got your individual pools for individual OpenStack services. How do you associate those with one another? So how do you actually link up those individual pools to rule sets that link to specific hardware? Again, this is slightly different between Joule and Luminous. In Joule, you would use Ceph OSD pool set followed by the pool name, and then crush rule set and a number, and in Luminous that has changed to crush rule. And oh, by the way, because Ceph is generally awesome, you can totally do that while your cluster is up and while there's I/O happening on the cluster, because what Ceph will treat this as is just a simple backfill operation. So you can at some point decide that, well, we originally had all of our Cinder data on spindles because that's what we could or wanted to afford at the time, and now it's a couple of years later and we can actually get NVMe devices for a price that is affordable for us. So now we want to move all those Cinder volumes from spindles to LVME. That's literally one command that we're issuing on the Ceph command line, and then everything gets migrated, and when it's done, it's just faster, which is pretty neat. The question may arise in like, okay, in what order of priorities do I do that? So if I've got a cluster, a Ceph cluster that is mostly spindles, and I'm kind of making the transition to all flash, what is a good order in which I should take my individual Rados pools? You probably want to start out with your Nova ephemeral pool, so whether that's called VMs or Nova Compute. The Rados Gateway Bucket Index pool is a very, very good candidate if you're using Rados Gateway as your drop-in replacement for OpenStack Swift. Then Cinder volume pools, Rados Gateway data pools, glance image pools, and finally Cinder backup pools. That's usually the last pool to convert to an all-flash, all-flash OSDs. Now, there is one thing that I do want to point out, and that is in a Ceph cluster or in a Ceph-backed OpenStack cluster, you might want to consider deploying some of your compute nodes, some of your hypervisor hosts with low latency local storage. Now, why is that the case? Because storage latency has dropped much faster over the past few years than network latency has. So it used to be in the olden days, like 10 years ago or something like that, we would assume that a single sector write to a spindle would be something that would take about a millisecond, and a typical gigabit or a 10 gigabit Ethernet network latency is about 100 microseconds. So that's an overhead of about 10% from writing locally to writing to something over a network. Well, now we're writing to flash storage at a single sector write latency that is an order of magnitude less, so that's also in the 100 microsecond ballpark. And so that means that if we're now going over the network to talk to some kind of storage, our overhead is more like 100%. It's still faster in absolute numbers, of course, but our overhead is larger than it used to be. And then if we add a facility that replicates some of our data out, and that also contributes to latency, then that can be quite substantial. The reason why I'm mentioning that is that because it's not necessarily such that most applications care about a lot of don't care much about a small latency overhead because they're not latency critical at all. But the bad news is that some will, and if you're operating an OpenStack cloud, then it's a little hard to sort of predict what kind of workloads your users will be running on those machines. So should you ditch Ceph because of that? No, absolutely not, but do consider adding a handful of compute nodes that are not configured with images type RBD, but that use local disk images instead. Nova then enables you to put these hosts together in a host aggregate, and you can map them to a specific flavor. And flavors don't need to be public, so what you can even do is you can say, well, by default, you get storage that has a certain amount of latency, but if you want actually low latency storage, then I'm going to assign this flavor to your tenant/project, and I might also pay you make you pay extra for actually running VMs in that tenant. And that's sort of the classic approach if you have customers that say, I need to run database application X with maximum write latency Y, and your Ceph-backed OpenStack cloud can't really provide that or can't really do that. The proper approach to doing that, because they will benchmark against local storage, and so that's something where Ceph is likely to just add, shall we say, not necessarily substantial but significant overhead. And so you can say, all right, well, fair enough. You can have you can use these local storage compute nodes where the latency is much less and you're achieving the latency guarantees that you're looking for, but just make sure that you take care of your own high availability because the storage is local and there is no protection against the loss of a compute node. Now, most database applications will be perfectly happy to take care of their own replication with MySQL Galera, for example. And then if you do want to put that out as a service, then you can, of course, look into Trove and see how you can do that. What else should you be doing in or with your VMs that use Ceph backing storage? You should configure your VMs to use VirtIO SCSI. So by default, RBD-backed Nova instances use the VirtIO block driver to expose RBD images to the guests as virtual devices. And so basically, it presents a virtual PCI device to a guest that represents a paravirtual I/O bus, and those devices are then named DevVDA, DevVDB, and so forth. VirtIO block devices are very lightweight and efficient, but they do come with a drawback. They don't support the discard operation. Not being able to use discard means that the guest can't mount a file system with mount o discard, and they also can't use fstrim to free up blocks on the file system. On the one hand, that might be a security concern for some of you users who might want to be able to really actually delete data from within the guest. But it can also be an operational concern for you as the cluster operator. Because if you're not supporting discard, then that means that Rados objects that are owned by the corresponding RBD image, they actually never get removed during the image's lifetime. They persist basically until the whole image is deleted. So your cluster may carry the overhead of perhaps tens of thousands of Rados objects that no one actually cares about anymore because the application has deleted them. But if an application deletes something in a file system, that's something that a block device typically doesn't care about, unless it's mounted with discard or you're running an fstrim operation on a weekly basis as a cron job. So thankfully, there is an alternative VirtIO disk driver that does support discard with RBD, and that's the paravirtualized VirtIO SCSI controller, VirtIO SCSI. And enabling that VirtIO SCSI controller is something that you do by setting a couple of glance image properties, namely HW SCSI model and HW disk bus. And this is how you do that on an OpenStack image. You just do OpenStack image set. There's these two properties, HW SCSI model and HW disk bus. You set those to VirtIO SCSI and SCSI respectively and apply that to whatever your image is. And then when you fire up a VM from that thing, then you're going to see a virtualized SCSI bus, which does everything that you expect it to do. So these devices will show up in proc SCSI. You can extract information about this with ls SCSI if you want to, and your devices are called SDA, SDB, and so forth. And importantly, you can now use those devices to support trim and discard, which is pretty cool. You should also consider at least setting disk I/O limits on your Nova flavors. Now, why is that? In a Ceph cluster that acts as backing storage for OpenStack, it's kind of natural that many OpenStack VMs do share the bandwidth and the IOPS and whatnot of your whole cluster. And when that happens, then occasionally you might have a VM that's very busy, meaning it produces a lot of I/O, and the Ceph cluster will attempt to process that to the best of its abilities. And in doing so, since RBD currently has no built-in production-ready QoS guarantees, there is work on this. There are some interesting patches that went into Luminous for the mClock QoS framework. But currently doesn't have that. And what might happen is you've got one VM that does a lot of work, and that might cause other VMs to suffer from reduced throughput or increased latency or both. And the trouble with that is that you should always think about your users. The trouble with that is that it's almost impossible for your users to reckon with that and to calculate based on that, because what they'll see is they'll see a VM that sustains, say, 10,000 IOPS at sometimes and then drop to 2,000 with no warning or explanation, just because there is a wholly different VM that does some work on the cluster. And so what you should consider is to preemptively limit your RBD performance from the hypervisor, and luckily Nova absolutely allows you to do that. That's a concept that is known as instance resource quotas. and you set those via flavor properties. So for example, you might want to limit a specific flavor to, say, 1,500 IOPS and a max throughput of 100 megabytes per second. You do that with OpenStack flavor set, and these properties are always prefixed with quota colon. And in this example, we would be setting 100 megabytes per second as the maximum throughput or the maximum bandwidth that we're allocating to this thing, and a maximum of 1,500 IOPS. There is separate settings here for disk read bytes and disk read read IOPS, and disk write bytes and disk write IOPS. And then we have the ability to limit it in total. And in the background, ultimately, those settings are handed through to libvirt, and they're fed into C group limitations for QEMU and KVM. And those are applied when the VM with this flavor spins up. So these limits aren't specific to RBD, but they come in very handy when dealing with RBD. I do want to point out that Nova only applies those on instance boot up, whereas libvirt does allow you to set them on the fly. The only reason I'm mentioning that is you may sometimes run into a situation where you're modifying flavors that are already in use, and then what you have to do is you have to go through your VMs, and if you want to make sure that those limits apply immediately, you would have to manually or script the application of that via the versh command. But Nova itself will only apply this when a VM is spun up. I believe, but I actually have to double check on that, but I believe it also applies when you change a flavor, so you do a resize operation. And again, since flavors can be public, but they can also be limited to specific tenants, what you can do is you can set relatively low instance resource quotas for your public default flavors, and then you can make flavors with higher resource quotas available to select tenants only. Which is probably a little easier on your resource utilization. And if you're a public cloud provider, that's something that you might charge a customer extra for. There's an equivalent to this, because this stuff obviously only applies to ephemeral disks. There's an equivalent to this in Cinder. You set Cinder volume types, and you define QoS profiles, and you can define disk I/O limits in those. So volume types, a lot of people use volume types to enable users to select a specific Cinder backend. But it's perfectly okay to define multiple volume types using the same backend, and then you can set characteristics like max IOPS or max throughput via QoS specifications. And just to be consistent, a QoS specification that applies the same limits as the one that I just showed for the flavor for ephemeral volumes would look like this. You do OpenStack volume QoS create. The consumer for this is always front end. And there are these two properties that we can set, total bytes sec and total IOPS sec. And then we give that QoS profile a name. And then we can assign that to a volume. I was being a little bit lazy here in giving the volume type and the QoS profile the same name. You might use a QoS or type prefix or something like that. By the way, volume types are actually exposed in Horizon, so the name that you set there is something that your users do see, and you may just want to make sure that that's self-explanatory. I want to get to something that is frequently overlooked in a Ceph or RBD-backed OpenStack environment, and those are suspend files. Who in here uses Nova suspend and resume? Have you used that before? Oh, yeah, okay, a few. What Nova suspend and resume does is not suspending and resuming a VM. Because most people would think that suspend and resume is just, okay, we're just going to essentially send a sig stop to the QEMU process. That's emphatically not what it does. What it actually does is what libvirt calls a managed save. So the instance's entire memory is written to a file, and then the KVM process shuts down entirely. And that's quite neat because it means that the VM doesn't consume any CPU cycles or RAM until it restarts. And then it will continue right where it left off, even if the compute node is rebooted in the interim, which is cool. And it also means that if this is in a public cloud, you're actually not paying for that, or at least you're not paying for CPU cycles and RAM because it's actually not running. And it's all, from the operator perspective, that's obviously nice on resources. But you should understand that these save files, they go to varlib nova save. they're not compressed in any way, so that can add up pretty quickly. So if a single compute node hosts something like 10 suspended images, the combined save file size can easily exceed 100 gigabytes. And frequently people are under the assumption of, oh, my Nova uses RBD storage and my Glance uses RBD storage, and so does my Cinder. So basically, my compute nodes can almost be diskless, save for the operating system. When you apply that approach, please don't forget about suspend files, because if your var file system on those boxes is only 8 gigabyte, then suspend files will slam that very quickly. Or worse, they might slam your root file system. Now, of course, if you already have a Ceph cluster, then you can put it to good use here too, because what you can do is you can just deep mount a cephfs into that spot, right? You just deep mount cephfs into varlib nova save for each of your hosts, and then boom, that's it. And then your suspend files also go onto your Ceph cluster. And now, snapshots. And this is a tricky one. So OpenStack makes use of RBD snapshots all over the place. Just to give a few examples, in ephemeral storage, if we're using Nova with ephemeral storage on RBD, and we're also using Glance on RBD, and we have the Glance v2 API enabled, and we're using show image direct URL equals true, then Nova will always clone from the image snapshot. So that means that immediately when we upload an image into Glance with the RBD backing store, RBD creates a snapshot for us, and it's from that single snapshot that all of the ephemeral disk for images are cloned. So that's just one snapshot per image, no more. Then we can do Nova snapshots. When we create an instance snapshot from Nova, since I believe Mataka, what RBD will do is it will create a snapshot image and then create a clone from that snapshot, and then by default flatten that clone so the snapshot can be managed independently of the VM. For those of you not familiar with clone flattening, it means that we're actually we're dissociating a clone from its parent, and it becomes a an image on its own. And the reason for that is that the parent is, of course, a VM, and that VM in OpenStack is by default ephemeral. And if we didn't dissociate, if we didn't break this link, then we could never delete the original VM that we created the snapshot from. So that's why we're doing that. But that's also not a great number of snapshots that is being created. But let's talk about Cinder. So Cinder volume snapshots also obviously map to RBD snapshots whenever Cinder is RBD backed. And also with Cinder backup, we might be using snapshots for incremental differential backups. And this is something that your users can control, and they might be creating any number of snapshots. But you should know that there is a little more to RBD snapshots that meets the eye. They look easy and straightforward on face value, but they're quite complex, and I'm not going to go into the details very deeply because there's an excellent video on this from Greg Farnham, who's a Ceph core developer from the Boston Summit. It's called Ceph Snapshots for Fun and Profit. You should totally watch that. But just a very brief summary, you should know and understand that while snapshot in Ceph RBD are cheap, they are not free. And snapshots are particularly affected by one internal detail of their implementation that can cause really, really bad side effects in the event that there's been a lot of RBD snapshots that have been created at some point, and subsequently many of them, but not all, have been deleted. Okay, so that sounds weird, but that's about what it is. And in an OpenStack environment, that's a little tricky because you don't really have control over how many snapshots, for example, in Cinder or backups, your users take and then subsequently throw away. You have control over how many they have because there's quotas for that. But if they're creating a lot and then throwing them away and then creating more and then throwing them away, then they never actually exceed that quota. And like I said, it's pretty complex. It's also fascinating. It's very interesting. Do watch that talk by Greg. And this specific issue that's mentioned in there, there is an ongoing thread on the Ceph Develop mailing list, and that is something that is being fixed. We're going to see how it's backportable to Luminous or how that can improve things. But it's a fascinating subject if you're a Ceph geek, and do dig into that. I had originally planned to have a few minutes for questions. I now see I have exactly 3 seconds for questions. That's not going to work out too well. So in the interest of the next speaker, I would ask you, if you do have questions, please find me outside. I'll be happy to hang around for half an hour. Thank you very much for coming, and enjoy the rest of the summit.